please.
Thank you. Thank you very much for the invitation. I'm really enjoying this very nice conference. I will tell you something about not generalized scalar or generalized complex geometry. So we seem to butcher your initial intended purpose of this workshop. Sorry about that. But as we already saw, these circle of ideas are actually closely related. So what I will explain today is based on two joint works with Barbaro, Lagdili, and Streets. The one was with Barbaro, Lee, and Streets, and I will refer to that as ABLS. And the other more recent is a joint work with Lagdili and Lee, which I will refer to IOL. So what I will explain today is a class of Hermitian metrics, which I unfortunately called Bismut-Ricci flat and pluriclosed. However, this pluriclosed is precisely the notion of SKT that we saw in Gilles Cavalcanti's talk and the previous talk. And Bismut-Ricci flat and SKT, but together are the notion that Mario just explained to us in the previous talk, this BHA. And I think in physics literature, you can encounter this type of metrics as Calabi-Yau with strong torsion. So this will be the object I will explain. Then I will discuss known examples and some sort of a no-go conjecture, Folklore conjecture, which was floating around. So we will see that that's not the case. I will explain a general principle for this Bismut-Ricci flat pluriclosed Hermitian matrix, which allows us, at least locally, to reduce to one dimension less. And I will use this reduction in complex dimension 3 to actually reduce the problem to a piece of Kähler geometry. So this is even more appalling for some of you, but today we'll be doing some sort of a Kähler geometry at the end. And using this piece of Kähler geometry, we will return and construct some global examples that were welcome and missing in the literature. So let me start. If you have questions, don't hesitate to ask while I'm talking. All right. So here is the definition. So what I will be considering is a notion that appeared in some physics works, although we saw in the previous lecture that probably physicists wanted too much. But anyway, so I will consider a complex n-dimensional manifold N, and I want the Bismut-Ricci form to be 0 and the manifold to be pluriclosed. So pluriclosed means that the Kähler form is Didi bar closed, and Bismut-Ricci flat means that the Bismut-Ricci form is 0. So I will recall here that the Bismuth connection is a Hermitian connection which has a torsion given by dc omega. So I will probably write here. So that this Bismuth connection in general is given by the Levi-Civita connection plus a torsion term. And the torsion term will be 1/2 h, where h is a tree form. H is the tree form equal to minus dc omega. So the pluriclosed condition tells us that this form actually is closed. The tree form is closed. Okay, so this is a Hermitian connection, metric and Hermitian. It has torsion. Nevertheless, it defines a representative of the Furchan class by this well-known formula. So that's the so-called Bismuth-Ricci form. So this rho B omega is a closed 2 form. So I will probably recall you that when you have such Hermitian connection, you have another Ricci form, which I will call Rich B. and it will be just another trace of this curvature. So I can also take a trace as we do for the Ricci tensor, for instance. And this, since we have a torsion, this will be different than ρ. Okay, so again, I will be interested in this situation when I have a Hermitian metric with pretty closed Kähler form and vanishing Bismut-Ricci. So why we do care? I think Mario's beautiful talk may probably convince you much better than I will try to do right now. But just to recall that Ricci flat Kähler metrics, which we call Calabi-Yaus, are examples of such a situation, and this will be trivial from the purpose of this talk. So I want really to ask for a non-Kähler extension of Calabi-Yaus. Also, one feature of this Calabi-Yau geometry is that it defines a Hermite-Einstein metric on the tangent space. So from that perspective, it was a very nice observation. I think the original idea goes back to Bismuth, but it was put in a very clean form recently by Mario, Jordan, and Streets. Which actually tells you that if you have a Bismut-Ricci flat pluriclosed metric, then what you can do two things. First of all, because of the pluriclosed condition, you can define a holomorphic structure, kind of a twisted holomorphic structure on the tangent plus complex cotangent bundle. So this d bar omega will verify d bar square omega equal to 0 because of the pluriclosed condition. So it defines a holomorphic structure, which is different than the natural holomorphic structure you may think of on this bundle. And the claim here is that if the Bismut-Ricci form is 0, then the induced Hermitian metric will be Hermite-Einstein on this bundle. So as you see, this Bismut-Ricci flat pluriclosed condition from purely mathematical point of view is a very natural generalization of Calabi-Yau. Okay, so then mathematically, it's a fun question, actually. If you think about it, of course, we want the Bismut-Ricci flat to be 0, so we need the first Chern class of your underlying complex manifold to be 0. However, if you want to find a pluriclosed metric on a complex manifold with C1, 0, it's not a trivial question, and neither is find a Hermitian metric for which Bismut-Ricci form is 0. So these two questions separately are interesting and have been studied a lot. So I'll give you, as an example, one result due to Grantchev, and Poon. They show that this kind of infinite dimensional many manifolds here, as you see, some directed sums of S2, S4, and S3, S3. Each of them has a complex structure that admits a pluriclosed Hermitian metric and another different Bismut-Ricci flat metric. So natural question is to understand whether these two conditions can be realized with a single metric. And the fourth remark I want to make is that if you think about how to find such pluriclosed Bismut-Ricci flat manifolds, there is not a natural let's say scalar PDE that you can solve as you do in the Calabi-Yau case, for instance. So the geometry is much more involved, and as far as I know, the main analytical tool of attack has been this Streets-Tian flow technique. So what Streets and Tian observe is if you start from a pluriclosed manifold, so you solve the pluriclosed condition. And suppose you have 0 first Chern class, for instance, then you consider this flow, this parabolic flow. It's given by flowing the Kähler form along the 1-1 part of the Bismut-Ricci form. So what I prove is that this flow is well posed. It has a unique solution defined for small time, and it also preserves the pre-closed condition. And of course, rho b omega t equal to 0 is a stationary condition for this flow. So you hope to study long time existence, and you hope to prove that this flow will converge to something, and this something should be such a kind of a pluriclosed Bismut-Ricci flat metric. So this is kind of the main analytical tool that people used until recently to try to generate. Unfortunately, there are very few examples of this, nevertheless. So the main example is this, what I call Samuelson geometries, but this example was discovered by Cavalcanti and Gautieri, I think, in the early days of generalized complex geometry. And it consists of taking a, let's say, simply connected Lie group, even dimensional simply connected Lie group, which has a compact quotients as group. So Samuelson proved that such groups submit left or right invariant complex structures. So the construction consists of taking a B-invariant Riemannian structure on such Lie group and take a left invariant and a right invariant complex structures. So if you have such a situation, what was checked is that actually this B-invariant metric with either of the complex structure J or I will be actually Bismuth flat, and it will be also pluriclosed. So as you see, this example solves our problem two ways with respect to J or with respect to I, and this is an instance of generalized Kähler structure actually, as we saw in the previous talk. And then what you can do with this simply connected Lie group, you can take quotients. So for instance, in small dimensions, if you do that, in complex dimension 2, you will discover S3, S1 as kind of a compact quotient that carries all this structure. Or in complex dimension 3, you will discover S3, S3, and for instance, S3 with 3 times S1. This will be compact quotients of such Lie groups, and they all will have such structures. So we have some examples of BRFPs given on such Lie groups and quotients. And of course, what was observed later on, in particular by Birenza, Fino, and Grancharov, is that it can take, of course, such a group, quotient by Calabi-Yau, and take quotient then. So we'll have some kind of a locally product examples of Lie groups with Calabi-Yaus in general. And the main problem of the theory, in my eyes, was that actually this was the only examples available for until recently. And actually, there was a question of the so-called no-go conjectures, which was the question asked if it is true that if you have a compact non-Kähler Bismut-Ricci flat pluriclosed manifold, then necessarily it's covered by a even dimensional Lie group times Calabi-Yau Kähler space. And this question or conjecture had some popularity. So these are some results that pointed towards something in that direction. So first of all, in complex dimension 2, there is a kind of an older result by Gudushon and Ivanov. And they show that in this case, the only possibility is to have a Hopf surface, which is isometrically covered by R times S3. So this question and conjecture was confirmed in complex dimension 2. And there were further works by Brienza, Fino, Grancharov, Barbaro, Pediconi, Tardini, which show that the conjecture will be true if, moreover, this torsion is nabla-B parallel. So, in other words, this conjecture this question can be rephrased of asking if existence of Bismut-Ricci flat pluriclose would imply that the torsion is parallel. Okay. So this is kind of a rough overview. So now I want to explain to you some kind of some very important feature of these examples, which, as you will see, would allow us to attack the existence problem from a different angle. So first remark I want to make is about torsion. So I will use in this slide the compact assumption. So I will use the compact assumption two ways. The first is to make an important remark on torsion. So the torsion H, so the J is integrable. So the covariant derivative for J is a deviation from the Kähler condition, and because of integrability, this object essentially is determined by H. Remember, H is this torsion term, tree form, and the tree form can be decomposed. So we can take the trace of this tree form with respect to omega. So this will create a one form. This was the Lie one form from the previous talk. So this is the Lie form. And trace this part. So that's pointwise situation. Now what I claim is that because of the pluriclose condition, somehow these two parts, the one form and the complementary, are interrelated. Actually, you can prove that. So we use the closeness of H. So Mario asked the audience where we use the closeness of H, and I think it's precisely at that point. So use the closeness of H to show that the norm of H, actually the whole torsion, can be expressed in terms of this one form theta. So it will be the codifferential of theta plus norm of theta squared. So in particular on a compact background, so this theta will be 0 if and only if H will be 0, if and only if this is Kähler Calabi-Yau. And actually, in the previous talk, we saw a kind of an argument using the Bismut-Ricci condition. I think Bismut-Ricci flat, that you cannot have an exact theta either. So anyway, so this torsion essentially is reduced to the Lie form. That's the first observation. Second observation is of a slightly different nature. It's about this Bismut-Ricci flat condition. So what I'm writing here is a general definition of what's called pluriclose gradient steady soliton. So a Hermitian pluriclose metric is called pluriclose gradient Ricci soliton if you can if the following identities are satisfied. There are two identities here. So the usual Ricci minus one form H squared. So this is the natural two zero symmetric tensor out of H, and the Hessian of F. So this quantity involves these three objects, and you have a similar identity on H. So these two conditions are equivalent to write this other Bismut-Ricci tensor that I defined at the beginning, and it expresses the fact that it's a Hessian of a function. So this is, by definition, is called pluriclose gradient soliton, and it was known by work of Streets and Ustinovsky. That such solitons, they are really solitons of the pluriclose Streets-Young flow. What that means that the vector field, which is theta minus df, is real holomorphic, and the flow of this V, when you move the metric by the flow, you will satisfy the Streets-Young flow. And also, in that situation, automatically GV is killing. So this is similar to Kähler-Ricci solitons of gradient type. So this is a definition, and the relevance of this definition to us is this key observation is that in the compact case, if you have a steady soliton for the Stristian flow, it must be actually gradient. So this is similar to Perelman result in the case of shrinking Kähler-Ricci solitons. And the argument essentially is that there is a special functional called entropy, which the flow tries to minimize, and when you have a soliton, the flow exists for all time, it will converge to a critical point of this functional, and the critical points of this functional satisfy precisely this equation. So this really uses the compacity in an important way. So, sorry. So the conclusion is that now, if I have a Bismut-Ricci flat pluriclose metric, it's necessarily a soliton because the flow is just stationary. And therefore, this generating real holomorphic vector field must be killing. So I'm now left with two killing vector fields, just as consequence of this argument. So I will put this in a little bit more clean way. So the first line is just what we discussed. So this was Stritzo-Stilovsky. And one can, so you have two commuting killing vector fields necessarily. And one can work out actually that these commuting vector fields are also parallel with respect to the Bismuth connection. So in particular, they have constant length, and up to scaling the metric, I can assume that they are unitary vector fields. And the situation now is kind of a nice for dimensional reduction. So I will decompose the tangent space of N as the span of V and JV plus orthogonal complement. And this orthogonal complement is, I will call the horizontal part. And you can see actually that the Hermitian structure restricted to H is transversal, so it's invariant under the generators of V. So at least locally, I can form a quotient, and this quotient will be locally a manifold, complex dimension n minus 1. So let me see. Yeah, so this lemma tells us that each time on a compact Bismuth-Ricci flat pluriclose manifold, I have these two killing vector fields of unit norm in the non-Kähler case, and I have presumably a reduction. And this result here tells us what this reduction really is. So I will go through this reduction more carefully because it's important for what will happen. So I have this two-dimensional non-Kähler Bismuth-Ricci flat. So this is a local statement essentially. I use the compactness to show the existence of these two killing vector fields, but this statement is just writing down the ambient geometry and N in terms of this reduced space M, which locally always exists. So the first condition you get is that the Lie form of the reduced metric is exact, and this F is precisely the F from the previous slides related to the soliton interpretation.
Sorry, Besti, MT is actually a manifold, or is an orbifold? What is this?
This is a local statement. So you have a foliation. You have a foliation, and I consider just some local leaf space. So locally is a manifold.
Okay.
Yeah. So globally could be anything. So this is a local statement which just express the geometry of the ambient space, the Bismuth-Ricci flat pluriclose geometry in terms of this transversal geometry, which locally is a manifold. So the first condition is that the Lie form is exact. The second condition is so this means conformally balanced in mathematical language. So the second condition, which I call the Young-Mills, it comes from, so it says that the trace of, okay, so probably just, okay. So I have these scaling vector fields, V and JV, and using the metric, I can introduce one forms. And these one forms will be connection one forms on. So through this reduction, I'm thinking of n as a principal R2 bundle over this local quotient. So so the eta, this will be a curvature term that I call FV, and the G eta is another curvature term that I call GV. So we can show that this FV and FGV are basic. So this is really a principal vibration locally. And moreover, these basic forms have constant trace. So this first condition comes from the fact that the Bismut-Ricci form, which is 0, when I evaluate it on horizontal with vertical part, is 0. Next is this what I call anomaly equation. It really expresses the fact that DDC omega is equal to 0 and tells us that DDC of the reduced Hermitian structure is expressible by this 4 form, which is cooked up from these curvature terms. And the third condition, for the fourth condition, is the Einstein-Maxwell equation, which I call. So you have this kind of so this is the usual Ricci of the reduced metric, of the transversal metric, minus its torsion tensor and the Riemannian Hessian of F. So that's what this notation means. So you get actually that this guy has to satisfy such an equation, which is kind of an Einstein-Maxwell type equation. And this is completely reversible. So this 4 equations on the reduced geometry, if I satisfy them for a function f, 2 forms f, then I can rebuild a 6 manifold as a principal R2 bundle with curvature FV, FJV. And it will satisfy the Bismut-Ricci pluriclose condition.
Besti, is it also the equation for the 3-form H is also satisfied like this star H plus?
Oh yeah, so you're right. So actually, what happens is that I'm cheating a little bit. It will be a consequence. It will be a consequence of the fact that the traces are constant.
Okay.
But yeah, so normally, so Mario was asking why I'm not putting this something like the star H. Just probably the star B, sorry. So there is a relation here, which is of that form. But this will be a consequence, as I claim, from the equations above.
Right, because we are in 4 dimensions and H is the star of the leaf form, I guess.
Yes, exactly.
Yeah. I have one question. Sorry.
Yeah.
Is these equations are all locally defined or they are like also globally true? I mean, for any transversal manifolds.
Yeah, so maybe the proper way to answer this is that all these equations make sense as transversal geometry. You know, in Sasaki geometry, for instance, people do that. So you can really define them in transversal direction as transversal geometry. But locally, around the point, you can take a neighborhood and create a slice for the leaves. And on that slice, you will define a Hermitian structure satisfying all these equations. And if, of course, for this V and JV, for instance, induce a T2 action and the quotient is an orbifold, this equation will be defined globally on the orbifold, as you will see in a moment.
So in general, these equations may not be invariant under holonomy.
They are invariant. These equations are invariant under V and GV. Okay.
This is in any dimensions. This theorem is
This is in any dimensions.
okay,
Yes.
okay, I was confused. Okay, so it's arbitrary.
Yeah.
Thank you.
Any other questions? So this is the first thing. So now let's explore a little bit. So the first thing I will do, I will return to Gudyushon-Ivanov result. Which is n equal to 2. So if I take n to be two-dimensional, then this transversal geometry or local quotient, if you want, will be a curve. So this is n equal to 1 here. And because of that, the first condition, the Lie form is always 0 on a curve, right? Because any Hermitian metric is scalar. So the first equation tells us that f is constant. Now the second equations were that the trace of fv is 0 on a curve, fv is a 1-1 form on a curve. This means that fv is 0. And the other condition was the trace with respect to omega t of fjv is -2. This means that fjv is minus the transversal Kähler form omega t. So the second set of equations, there was fv 0, fgv is -. The third equation, the anomaly equation, is trivial here because it's a 4 form on a curve. It gives nothing. So what we conclude so far, f is constant. Of course, the torsion is 0, and fv is 0, and fgv is minus omega t. So now we'll go to Einstein-Maxwell equation, which I recall was this Ricci j omega t. And just to remind you, this twisted Ricci operator, it was defined by this formula, but I already proved that this guy is constant, and this is 0, so it will be the usual Ricci tensor. So if we go to this fourth equation, it will give me, so this term is 0, so this will be minus omega t square, which is gt. So what I get is that this will be Einstein with positive scalar curvature, so it has to be P1, and we recover the result. So now what I will do, I will go to complex dimension 3 and also analyze a little bit more carefully the reduction. So we are now in complex dimension 3, and this is the reduction is a complex surface, and you see equal to 2 here. So the first condition tells us that the reduced Hermitian metric is conformally balanced, but balanced in complex dimension 2 means scalar. So what I get is that I will have a Kähler metric in the reduction. So I can define a transversal Kähler structure by this formula. So that's where complex dimension 3 is important, because the reduced space will be conformally Kähler. So it will be in particular Kähler. Then the Young-Mills condition, I can rewrite this condition with respect to this conformally Kähler metric. So this Young-Mills condition, I do nothing but just writing the trace with respect to omega kt, which is the Kähler metric. And if I do that, it turns out that I will get minus twice exponential of f, just by the very definition. This is for FGF, and for the other curvature form, the trace will be 0. So the anomaly equation is very important, but I will do nothing for the moment with it. So this will be kind of really the important equation. But I will now stare at the Einstein-Maxwell equation. And with a little bit of massaging, it could be written as the fact that this second curvature, whose trace was negative, is equal to minus the Ricci form of the Kähler metric. So again, I kind of rewrite everything with respect to the Kähler background rather than this reduced Hermitian. So from here, I have a conclusion. So this is something that we establish in the first of the papers, is that in complex dimension 3, this Bismut-Ricci flat pre-closed manifolds, the transversal geometry reduces to a special type of Kähler geometry. So first of all, okay, so probably I will get back here. So from here, I can deduce that because this is the rho, so I will reduce that. This will be the scalar of omega k, which of course is the trace omega kt f it's minus fjv. Okay, so because of that, f must be the scalar curvature of the twice exponential f must be the scalar curvature of the Kähler metric. The Kähler metric has to have a positive scalar curvature, and this is the this anomaly equation that I am left with, which now just remind you. So this beta will be our fv. It will be a 1-1 form, which has zero trace. That's a primitive 1-1 form. In complex dimension 2, this will be also anti-cell duo harmonic form. So this is the BT, and I have such a situation. And conversely, now I had questions about global, not global. Suppose actually that I have a complex surface that satisfies this condition, and suppose furthermore that the RAM classes of this beta and C1, which is just the RAM class of rho omega kt, admit a Z basis. Then what I can do, I can take a principal T2 bundle over this Kähler surface, compact Kähler surface. I will get a compact 6-dimensional manifold, and I can pull back the geometry from the surface upstairs by the recipe you saw before, and I will construct a Bismut-Ricci flat pre-closed tree manifold out of such a complex surface. Is there questions at this point? So I can reverse this whole construction once I understand well the reduction. Okay, so now the next slide, I will take the point of view that this reduced space, this local quotient is global, and we'll assume for the moment that it's a compact Kähler surface. Now I want to set up a PD problem. It's familiar in Kähler geometry, and try to find examples of such Kähler surfaces. Okay, so that's the purpose. What I will do, I will fix the omega. So omega will be the Durham class. Let me see. Will be fixed the RAM class where omega kt will be found. Okay, so this will be the Kähler class of the reduced geometry. I will fix another 1-1 class, which will be the class probably 2p, just to be sure, where this beta will be. And then the reduction tells me that I want to find a Kähler representative, Kähler metric in this capital omega, which solves this equation. And beta h here will be a harmonic representative of this class B with respect to the moving Kähler metric. So omega phi will be a metric in the fixed class. So I fix one reference metric omega 0. So any other will be d bar of a function. So these are all Kähler metrics in capital omega. And I want to find one which satisfies scalar curvature positive and satisfy the reduced equation star. And in this reduced equation, notice that the beta will be just the harmonic representative of 2 pi beta because of the conditions I said here. Harmonic form with respect to a Kähler form has a constant trace. Because of this cohomological condition, this trace will be 0. So this harmonic representative will be automatically closed and primitive with respect to omega phi. So this way I set a single PD for finding Kähler geometry on the reduced space. So this is a PD for the potential function phi. And Well, of course, I did this on surfaces, but I can consider this PD in any dimension, taking star. If I take Hodge star, so this is a relation of 4 forms on 4 manifold. If I take star Hodge with respect to this, I will get this PD that I can consider in any dimensions. So on any Kähler manifold. Now, this PD is a 6th order. Of course, when you see such things, you wonder what's going on. However, I will tell you some interesting stuff now. I know. In the beginning, we didn't even know that. So first of all, we can allow for this PD, instead of having 0, to have a constant here. I will take constant. And I can also consider kind of a special case where this is 0. So this PD now, with beta term 0, this is an example of what's called Z charge. PD, which is studied by Derva around 2002. For example, a special solution is so if omega is 2pc1m Fano. In this case, I can take Kähler-Einstein metric. So Kähler-Einstein metric has, of course, constant scalar curvature, so this term will be 0. This norm of Ricci will be constant, and scalar square will be constant, so this will be a solution of this modified Z-charge equation. So Kähler-Einstein metrics are examples. And I think from that perspective, it has been studied by Shushon Chen and Tian. At the time, they were friends. They have even a paper in Duke about this equation. So anyway, so from Kähler point of view, something interesting is going on. And I am putting here the upshot of some more recent work that we did. So it essentially will tell you that this PD can be interpreted as a moment map. Here is the setting. So again, I assume this reduced space is a manifold or an orbifold, and then I consider I fix a Kähler metric in omega Kähler. And now I consider all compatible almost complex structures for which the scalar curvature, this means Chern scalar curvature for the non-integrable ones. The Chern scalar curvature is positive. So this is a kind of a formal Frechet manifold. And on this formal Frechet manifold, Donaldson and Fujiki constructed a complex formal integrable complex structure. So this is an infinite dimensional space. So I consider all almost complex structures on my manifold M, which are omega compatible. So all these almost complex structures have a formal complex structure, and this formal complex structure at a point J to a tangent vector J dot, which is kind of an endomorphism, will just give the composition of the endomorphism with J. So this is an integrable complex structure. And then I act with the Hamiltonian transformations. This will be M here. With the Hamiltonian transformations with respect to omega. And what we do now, we kind of introduce a new symplectic form, which is J compatible, so new formal Kähler structure, for which this action will be Hamiltonian with momentum map given exactly by the PD. So this PD has a momentum map interpretation, and for those of you that are curious, I define just below how this formal symplectic form looks like. So for instance, if I didn't have this scalar curvature term, if this scalar curvature term was equal to 1, and all the remainder was 0, this will be the original Donaldson-Fujiki symplectic form that interprets the scalar curvature as a momentum map. But now we introduce this additional term, scal J. That's why we want this condition to happen. So this is kind of a positive definite. And then we have additional terms which are given by some divergence terms with respect to the tangent vector, and another pseudo-differential part which involves this harmonic beta. So anyway, so this is kind of a fun situation that you have this moment map interpretation, infinite dimensional moment map interpretation of the problem. And why we bother about this moment map interpretation? So because we have a toolkit from this problem of constant scalar curvature metrics, this Calabi problem that has been worked out by Tian, Yau, Donaldson, and from this theory, we know that once we have this GIT interpretation, we have many good things. So, for instance, we have Calabi-Lishchenrovitz-Matsushima theorem. So, if I have a solution, even of this more general problem in Kähler geometry, the 6-dimensional PD, I know that automorphism group is reductive, and the isometry group of a solution is a maximal compact of this reductive group. For instance, I will use later on that for rational root surface, for instance, first Hirzebruch surface. The automorphism group of first Hirzebruch surface is not reductive, so you cannot find solutions on first Hirzebruch surface, for instance, or on P1. Here we know that the solution must be invariant under a maximal compact, so it must be invariant under PU2. So it must be a product of constant scalar curvature metrics. So I have a uniqueness. Also, from this general picture, you can derive a Futaki invariance. So we can rule out certain Kähler classes if you wish. So all these nice properties that we know from constant scalar curvature problem now extend to this more general problem. And here are the two results that I want to discuss briefly because my time is pressing, I think. So these two results, first is kind of a rigidity, assuming regular. Regular means that n mod V is a manifold, smooth. So in the regular case, what happens? So first of all, we have general Bismut-Ricci flat pre-closed threefold. We previously observed that the Bock-Chern 1-1 cohomology, the dimension of this is at least 2. And somehow, if you want, the minimal case is when it's 2. So these two results concern the minimal case. And in the regular situation, when the quotient is smooth, we can actually show that the only examples are Samuelson examples. This is the rigidity. And then we have also existence of examples which are not locally homogeneous at all. And they're not regular, but they're quasi-regular. Which means that this leaf space is an orbifold. But actually, these examples could also be made transversally, so there are even irregular ones, if you wish. So these are the two results. So the first result, the rigidity, how we get the rigidity. So now the assumption is that the reduction is a smooth manifold. And in this case, it's a smooth complex surface. And we know from the equations, first of all, this H11BC condition, it's equivalent to the assumption that the second Betti number is equal to 2 of this quotient, on this 4 manifold. And now we have a complex surface with positive scalar curvature. It's a well-known result going back to Yau in the 70s, I think, that the Kodaira dimension of such a surface is minus infinity. This means that there are no sections of powers of the canonical bundle. So you don't have sections. In particular, H20 is 0. But B plus for a complex surface, Kähler complex surface, is 1 plus twice H20, and is equal to 1 in our case. So this condition implies Kodaira dimension is minus v, and b plus is equal to 1. But since b2 is equal to 2, then b minus is equal to 1. And therefore, the signature of this complex surface is 0. And you can look now in the Kodaira classification list. The only possibility is to be a ruled surface, ruled complex surface. But remember, this PDE that I have, if you integrate it, the PDE, where was this? Okay, so here. So if I integrate this PDE, I get this topological relation, which essentially determines the B, if you wish. So because of this, I have something to say about the sign of C1 square. In our case, C1 square has to be non-negative. And again, the only ruled surfaces that satisfy this are ruled surfaces for which the base is either P1 or elliptic curve. And now we use this Matsushima-Lishnerovich theorem that I told you. If C is P1 by Matsushima-Lishnerovich, the only ruled surface, a rational ruled surface that has reductive automorphism is this one. And on this one, we know that the solution must be invariant by PU2. And we get here for the sixth manifold something which is S3 Samuelson. And similarly, in the other case is a little bit more complicated. But again, if we are ruled surface over an elliptic curve, then there is an extensive work by Suva, who determined the automorphism group. And going to Suva's lists, you see that only possibilities is that this vector bundle that you projectivize is polystable. And furthermore, when it's polystable, of course, by Narasimhan Ramanan, you know that there exists a locally symmetric solutions of your problem, which are locally product of constant scalar curvature on the base and constant scalar curvature on the fiber. And you have to prove that these are the only solutions. And here again, we use the Matsushima-Lishnerovich, because by Suva, in such a situation, you have a non-vanishing holomorphic vector field. And by this Matsushima-Lishnerovich result, it has to be parallel. So you get a local product structure, and you do some routine work to show that all solutions are such kind of a locally constant scalar curvature products. So that's how the rigidity result follows. So now I will tell you the existence. So the existence is under assumption that this reduced space is a toric orbifold surface, and we will assume that it's toric, that it itself has a T2 symmetry. So the six-dimensional manifold I will build will have T4 symmetry. So this quotient space has T2 symmetry, and when I turn on V and JV, this principal T2 bundle, I will get to T4 symmetry. So this is a toric, and toric orbifold surfaces are defined in terms of dosant momentum polytopes. The fact that I have B2 equal to 2, this gives me that this dosant polytope has to have four summits, so four vertices. It has to be a quadrilateral, and I will assume that it's a generic quadrilateral, no parallel. So when I have such generic quadrilateral, so I guess I have to put, this is my, oops, sorry. Yeah, so this will be my delta. So this will be the dosant image. So for such quadrilaterals, what you can do, if I take a point in the quadrilateral, I can join it with these two intersections of opposite faces. So this is a point inside, and then I will measure the angles. This angle I will call it X, and this angle Y. So what I get is a map from something which I call x1, x2 times, so product of intervals to delta. And that's what I would call factorization structure. So why I'm doing this? Because if I have a such factorization structure, I can use an ansatz for constructing a compatible Kähler matrix, and this is the so-called ambitoric ansatz that we have been developing in the past for the purpose of studying extremal or constant scalar curvature Kähler matrix on such objects. So we kind of adapt the whole machinery to our new problem. So here the metric is so this part is the reduced metric on the inside the polytope. It will depend on two functions of one variable each, and these variables x and y will be precisely these angles that I called. So and then you have kind of orthogonal part, which is on the torus. I didn't specify here, but the Kähler form is of that sort. So essentially, this part will be this guy squared plus this guy squared, a little bit mangled with A and B. And the whole point of this ansatz is that I can write down explicitly a harmonic primitive form. So this thing is a harmonic primitive form. On a general polytope, using this Abreu-those Gilman formalism, you will be not able to find such harmonic primitive forms explicit. But in this ansatz, I have it. And now the miracle. The miracle is that if I look for a solution of my sixth order PD of that particular ansatz, so I plug in here, it turns out that there is a very simple solution when I take each of these A and B to be just quadrics. There's polynomial of degree 2, which vanish at the endpoint on the intervals. And then you could just satisfy, so once you plug this, the PD becomes an algebraic relation from which you can kind of agree these coefficients A0, B0, and lambda. You just express lambda as a function of A0, B0 if A0, B0 are suitable intervals. And I can do this over the rationals. So I can take this x1, x2, y1, y2 to be rational numbers. So this will be rational polytopes. And then I will have an orbifold. And from this orbifold, you kind of you have to work a little bit to show that how from this orbifold you can get a smooth fibration. So there exists a T2 bundle over this orbifolds, so with smooth total space. So this is kind of a key observation. So I will probably leave this last part because the time is pressing. So thank you very much.
Hey, thanks for the very nice talk. Are there questions from the audience?
Yeah, Vesti, thanks for the nice talk. I had a question going back to this set critical story that you mentioned, Ruiz thing. So you mentioned that you had a moment map interpretation and that there's a Kähler form that you obtain for which this is a moment map. So Durbin and Hallam has a paper where they show that set critical things in general are solutions to a moment map equation for a not necessarily positive form. So how does this relate to that? Is it the same form and you show it's positive, or is it a priori something that could be different?
Yeah, that's a good question. Yeah, so that's right. So Der van Halen. Oops. They have a moment map interpretation for Z charge. So moments. For more general for Z charge. So the problem is that the following. So this momentum map, their momentum map is defined on the same space M, and they define a symplectic form which to my knowledge, right. So the question is whether this is equal to the symplectic form we define here. Okay. To be honest, I don't know. So the first thing is that in this interpretation, it is not clear that this closed two form. It's a 1-1 form, a 1-1 form. It's not clear. It's a Kähler form. In our case, in order to be Kähler, we impose this condition. So presumably, the question here is whether the restriction of their form on this condition, on this M plus space, will agree with our form. And to be entirely honest with you, I'm not entirely sure. I think we tried to check this even I think one feature of this form is that it satisfies something like this, the of the Mabuchi energy. So even on that, even on restricted on an integrable complex structure, we tried to check this equality, but we didn't succeed to get it right. So it could be that we just didn't do the calculation right. So it's a computational intensive, all this stuff. But yeah, I don't know. I don't know if they agree. It would be very nice to check that they agree. It will really clarify the positive definiteness of their form, and probably this will extend to other Z charge. By the way, the Z charge is it has many parameters. So we have a Z charge for very special choice of parameters. Probably all this game can be played for any Z charge. So you can have a honest symplectic form in general for Z charges, which correspond to some sort of a positivity condition. So in our case, it's positive scalar curvature in general will be positive of some geometrical expression. Yeah. So, but I don't know.
Okay. Yeah. Thank you.
Well, I have also some questions. So in your construction of the new compact examples, do we expect that we only have Complementary Bismut-Ricci flux and free closed structure?
Okay. Yeah, I don't expect any finiteness results. For instance, a good kind of a working question will be the beginning of the slides. I listed this result of Grancharov in Grancharov-Pun. They have a list of manifolds on which you could seek for. So this, by the way, these are fibration over. So these are T2 bundles over rational surfaces. Yeah, so already I think we were trying to prove with Frédéric Rochon and with Lee some sort of a Rezzo-Packard type result. So for instance, it would be nice to see that you could use this minimal ones that we constructed to blow up and to find solutions on blow up manifolds and probably fill in infinite many diffuse types. Yeah. So I would expect it would be infinite many. It's really like Sasaki geometry here. You know, we're doing with the quasi-regular Sasaki structures satisfying some sort of a PDE. So this would be something very similar. So I don't see why they will be finite many, but who knows? You know,